Okay, so now on page 637. Okay, page 637, number 12. So it says, in an accident in a research lab, a radioactive isotope with a half-life of 3 days is spilt. So T to the 1/2 is 3 days. Okay? As a result, the radiation is 8 times higher the maximum permissible amount. So it's saying that whatever the permissible amount is, after 3 days, as a result, the radiation is 8 times higher the maximum permissible amount. And then it wants to know how long before they can enter the room. So in other words, how long before the activity, final, is the permissible amount. So if we call the final the permissible amount, then the initial is 8 times that, or 8 times what you want it to be in the end. Okay, so it doesn't tell us what the permissible amount is, but it tells us that whatever that is, when it starts, it's 8 times bigger than that. And then it wants to know how long before it gets to this permissible amount. So we're looking for how many half-lives need to pass. So if we know AF is equal to AI over 2 to the n, then we know 2 to the n is equal to AI over AF. And so if AI is 8 times the permissible amount, and we want to end up with the permissible amount, we have 2 to the n equals 8, because the permissible amounts cancel out, which means n is equal to 3. It tells us in the question that the half-life is 3 days, so we know n is equal to delta t over t to the 1/2, so delta t is just equal to n times t 1/2, or 3 times 3, so it's 9 days before the level will reach the permissible amount. Okay? Number 13. In a half-life of an isotope is 2 years. What fraction of the isotope remains after 6 years? So if the half-life is 2 years and the total time is 6 years, then n must be 3, right? 6 divided by 2. So it wants to know what fraction remains. AF is equal, or M if you want this time, you want to talk about mass, mass F is equal to mass I over 2 to the n. We don't know what the original mass is, but we know it's 2 to the 3. 2 to the 3 is 8, so how much of the original mass? 1/8, right? 1/8, whatever it started with. Okay? Number 14. The half-life of strontium-90 is 28 years. I'll just start a new sheet, it'll be easier to see. Is 28 years. After 280 years, what would the intensity of a sample be? So we have the half-life is 28 years. We know the total time is 280 years. So we get n to be 10 half-lives. So then it wants to know how would the intensity of a sample of strontium-90 compare to its original. So this time you can use, if you want, IF is equal to I initial over 2 to the n. So it doesn't matter if you call this an M for mass, an A for activity, an I for intensity. It's all the same equation. And really, again, it wants to know a fraction. So it's just saying whatever the initial intensity was over 2 to the 10th. And 2 to the 10th, if you do it out on your fingers, you do 2, 4, 8, 16, 32, 64, and you keep going, you eventually get to 1024. So it's equal to 1 over 1024 times whatever the initial is. If you want to do that as a number, then it'll be 0.0009766 times I. If you want to put that in a percentage, multiply by 100, and it'll be 0.097656% of the original. Okay, so not quite 0.1% left. All right, number 15, Geiger counter registers an initial reading of, now, so this time they're going to give us the number of counts. So we'd say CI, the initial number of counts, is 3,200 counts. Measuring a radioactive substance, and 100 counts, CF, 30 hours later. Delta T, 30 hours. So then the question, what is the half-life? So the first step is to find the number of half-lives. So CF is equal to CI over 2 to the n. So 2 to the n is equal to CI over CF. So 3,200 counts over 100 counts, or 32. And you should recognize 32, 2, 4, 8, 16, 32. N is equal to 5. If you don't know how to do it, if it's a number that doesn't work out nicely, you would then have to do, okay, so 2 to the n is equal to 32. Take the log of both sides. So n log 2 is equal to log 32. So n is equal to log 32 over log 2. And weirdly enough, that works out to be 5. I didn't punch it in my calculator. I'm trusting it does. So we have a half-life of 5. We have a full time of 30 hours. So we know that n is equal to delta t over t 1/2. So t 1/2 is equal to delta t over n. So 30 hours divided by 5, we get a half-life of 6 hours. Okay, so hopefully these are becoming pretty easy. I did realize that what might mess you up was like counts, activities, masses, but just treat them all the same. Number 16, a 14 grams, so we're going back to mass. So 14 grams. 14 gram sample, so that's my I, of carbon-14 contains Avogadro's number of 6.02 times 10 to the 23 nuclei. A 5 gram sample, M final, 5 grams, will contain how many non-decayed nuclei, and it's telling us the delta T is 11,460 years. Okay. So from this we can find our half-life, or find our number of half-lives. Delta T over T 1/2. And so 11,460 years. Well, what are they asking me? Yeah. And if you look up carbon-14 on the chart back here, before I run out of time, the half-life of carbon-14 is 5,730 years. 5,730 years. And so when you divide, I think that's 2. Okay, so we have 2 half-lives. So now if we go back and say, what the heck is all that mumbo-jumbo about number of nuclei? So a 14 gram sample contains Avogadro's number of 6.02 to the 23rd nuclei. A 5 gram sample will have how many non-decayed nuclei after 11? Yeah, okay, so this is not really your MI. One should read this closer. Okay, it's just telling us how many nuclei. So if 14 grams has 6.02 to the 23rd nuclei, then a 5 gram sample, you need to do a ratio, right? So take your